Hello, my name is Christian. I'm here to talk about magnetic shielding for spacecrafts. So a quick overview is why we desperately need it in space. So some of the health concerns you're going to have to worry about if you don't have it. Types of radiations you're going to have to worry about when you're there. And then what's the difference between active and passive shielding. And then some toroid shielding concepts that are used in monitor designs now. And then the pumpkin shield configuration, which aims to fix some of the problems toroid shields have. And then to finish off, I'll show you a solenoid shield design just to make sure you guys know toroids aren't the only thing we use in space. So health and safety problems. So if literally anything goes wrong in space, your chances of survival tend to nosedive. So the types of radiation exposure problems that rise are cancer risk, damage to your central nervous system, radiation sickness, and damage to electronics. So literally, if anything goes wrong, it damages your life support and things like that, and then your ability to fix things as well as like do your job while you're in space. So the types of radiation you'll encounter are solar particle events. These come from your solar flares and coronal mass injections. They're all described as high energy particles, but these tend to be more in the medium energy range from 10 MeV to a 1 giga-electron volt. And these events last several hours all the way up to a few days. And then there's a galactic cosmic ray. These come from outside our solar system. They usually come from more explosive events such as supernova and things like that. These are the high energy particles we have to worry about, but we're going to use our active shielding for. And then lastly, there's Van Allen radiation belts. And these are just ionized particles trapped by our Earth's magnetic fields. So active versus passive shielding. So the neat thing about passive shielding is that it's out of sight, out of mind. You kind of just keep it there and it'll do its job. It'll protect you from like your alpha, beta, and gamma radiation, things like that. But the problem is they're heavy. You can't exactly send a giant block of lead or concrete into space without it costing a lot of money. So what do we do to fix that? We get active shielding. This is the kind of shielding that you can turn on and off by essentially inducing a current into a solenoid or toroid, and it generates a magnetic field that'll help deflect particles away. This is the kind of shielding that can be adjusted to the user's needs. So maybe your space weather isn't so hefty this time around, so you don't need to pump your shield full of power. So some basic toroid shielding principles are the fact that they mainly use the Lorentz force, and the magnetic field is just found using Ampere's law. So basically, you just surround your habitable area with a giant donut. The effectiveness of active fields depends on several factors, basically the strength and orientation of the magnetic field and the velocity of energy of the charged particles that are incoming, as well as the geometry and materials you use for the shields. Here we can see basically the bending power of our shield. It's the Kasai equation number 3, but typically it's more useful to essentially describe our bending power from the particles properties just to see what is necessary for the shield at that time. So obviously it's the most penetrating particles are the ones that are coming in radially. So we just need to consider theta as 0. And the last equation is the maximum kinetic energy that our shield will need, essentially, where theta is the number of nucleons of the particle that is coming in, say iron, something like that. So the problem with toroid shielding is that high energy particles can come in and then get trapped within that magnetic field, creating a secondary belt of ionized radiation. So what we can do is, as well as causing inward forces towards the center of your habitable area, basically slightly crushing you a little. So one configuration that is aimed to solve it is the pumpkin configuration. So those inward forces are being supported and basically distributed using 4 central bars that hold 3 toroid racetracks, essentially creating a mime in a box, you'd figure, just completely wall to wall. It helps limit the secondary particle generation by restricting the cross section between the primary particles that are coming in and the materials of our shield. And this creates a more non-uniform magnetic field distribution. The problem with this is, or the problem with solenoids is this can't really be done with solenoids. But it's problematic with toroid magnets mainly due to the structural need to support the inward forces. And then lastly, I just wanted to show you that toroids aren't the only one out there. It's a solenoid shielding. So this one's actually cool. It's much like, I guess you could figure like a stack of cups essentially, and it basically collapses on itself, and you can either extend it or retract it based on your needs for shielding. It's the Magnetic Architecture and Active Radiation Shielding Study, MARS. It can be extended or retracted, obviously to change its size and shape and its flexibility to adapt to different spacecrafts, while minimizing its weight and power needs. Toroids are often used for more high energy shielding, so solenoids are not. They are more low frequency interference. This is something you'd find on like a satellite near Earth rather than your trip to actually Mars. That's all I really have for you. So here's a few references. Anyone have any questions?